Hi everyone. Thanks for turning up late on a Friday. As software consultants, it's quite rare that you actually get to work on an exciting project, technically interesting, but also that has a real impact in terms of environment and people. So we're really excited to be able to present to you today how to combat illegal phishing with machine learning and Azure. My name's Jess Panni. I'm a principal consultant at Engine. Carmel Eve is a third-year associate at Engine. Carmel will be taking you through some of the more practical elements of the talk in a while. I'll just do some introductions. So what are you going to learn? Well, when we first put this talk together, we had a slide deck that came to about 300 slides, I think. And we showed it around some people, and they said, look, you've really got to cut some of this out. So it was a real challenge to actually sort of cut this down into sort of a series of messages which we thought were going to be really important. So we've focused on 2 or 3 really key messages. The first, obviously, is what's the problem? What is it about illegal phishing that is an issue? We're then going to focus in on commodity computing, and we're going to try and explain to you why we think that not all serverless offerings are the same. We are then going to outline an approach that we took for solving this problem. We think it's a really important aspect of the talk. It really sort of dives into how to approach planetary scale compute, especially when you're looking at low cost, and this was really important for this project. Carmel's then going to talk you through how to build a real end-to-end scenario. She's going to show you some code and how that all works together, and then finally she's going to talk you through some of the lessons learned, things that we found were really, really helpful that we think would be useful for you to know. So what is the problem about illegal phishing? Well, I, for one, didn't really appreciate the impact that illegal phishing was having on the environment and on people. If we look at some of the statistics, 3 billion people rely on seafood as a source of protein, which I had absolutely no idea about when I first started. A third of all fish stocks are no longer biologically sustainable, which is devastatingly sad. 1 in 5 fish sold is caught illegally, and that's nearly $24 billion worth. And also there's other things going on, like there's a strong association with other criminal activities, such as people trafficking, illegal salvage, and those types of things. So we were really fortunate to work with a company called OceanMind. Their mission is to solve these problems. They do this by collecting billions of data points around the world. They run a whole bunch of AI machine learning over that data, and they identify illegal phishing activity. They compile information for law enforcement, for seafood buyers, for responsible, sustainable fishing products. So they're a fascinating organisation who are incredibly motivated. This is a picture of their NASA-style mission control centre. This actually takes up a massive sort of wall sort of size at the end of this room, I suppose. And each of those dots you can see there are vessels, they're boats. And you can see the outline of the continents that the boats are making. You maybe make out the major ports as well. So there's an awful lot of activity that's going on in the world. This is just one of their applications, which is great. You can zoom in. You can actually go down to an individual vessel. You can play that vessel, the track of that vessel over time, see where it's going, seeing how it moves. And they retain a lot of data behind the scenes. They can rewind, they can replay going back many, many years. They have other applications as well, such as applications that their analysts use to correlate information before forwarding it on to the authorities. So, how do they do this? Well, first of all, they gather vessel telemetry data. All vessels over a certain size are required by law to broadcast their position and information about who they are at regular intervals. OceanMind also use satellite imagery to correlate what they suspect is happening with actual pictures of oceans and vessels in places that possibly they shouldn't be. They also use radar imagery. And they take all this data and they feed it through some quite advanced geo-spatial analysis models. And what they're doing here is they're doing a lot of feature engineering. There's a lot of heavy lifting feature engineering which is going on that then gets fed into their machine learning models to go and actually detect, okay, what type of phishing do we think is happening in this particular region? And is it legal, is it not illegal? Those phishing alerts are then used through APIs and integrations to drive the systems that they use. So they're like any other organisation, really. They've got business drivers and constraints. What I love about OceanMind is they've got this really great passion for solving problems of this nature. And they really see their technology as being key to solving a whole bunch of other problems, like I mentioned, human slavery, people trafficking, those sorts of things. In order to do this, they need faster, more real-time alerting. They need more sophisticated AI and more AI. They want to start engaging and collaborating with people outside the organization, so sharing the story, I suppose, sharing some of the problem so that people can engage, collaborate. But they're a small organization, they're a not-for-profit organization, therefore they've got budget constraints. Their current systems run on-premise. There's no room to scale those systems. And a lot of their time was taking up just tackling fires and not enough time innovating. So the decision was made to migrate to the cloud, and that always is easier said than done. There's just so many different approaches, so many strategies you can take. And that's where we came involved to try and help them sort of on this journey and look at how they could actually do this in a smart way. One of the first conversations we really need to have is this: how are we going to do this migration? If we look at sort of the cloud evolution, OceanMind were very much classic on-premise. I mean, literally on-premise. They were looking after the building security. They were looking after the servers. They were provisioning those servers, looking after operating systems and the application logic. And obviously, that takes a lot of time and a lot of effort. We could look at lift and shift, an evolution in the cloud. Lift and shifting workloads can work. Problem with that approach is that they're going to be taking all the baggage of their architecture that they have on-premise, which has limitations in terms of scale, and just replicating that in an IaaS environment. And of course, more recently, we've got PaaS and we've got serverless, which is being talked about an awful lot. And we're promised that if we can migrate from on-premise to serverless, the potential for cost savings and general effort is quite significant. The problem is, I think, a little bit with serverless is that it's becoming a bit of an overloaded term. I prefer to think about it in terms of commodity computing, because I understand commodity services. I use commodity services every day. Who in the room has a smart meter? Okay, so for those of you who maybe aren't from the UK, there's been a massive push recently for smart meters, smart energy meters to be installed in homes. And the idea behind this is that if you can see what you're consuming, then you're incentivized, seeing how much it's costing you, you're incentivized to reduce your energy usage. So, I mean, that's the kind of approach, that's the kind of model we can apply to cloud computing. But most cloud services aren't actually like that when you think about it. For example, I plug in my kettle to make myself a cup of tea. I've actually got very used to, before I had the smart meter, I used to fill up the kettle all the way to the top and put it on. Now I've got a smart meter, I can actually see the money burning down. I actually make sure that I've only got enough water in for the number of cups that I want. I'm getting quite good at that. But in cloud computing, quite often, you have to pre-provision capacity. Okay? So that's a bit like saying that, okay, well, on average, I consume about 30 kilowatt hours per day. So I go up to my energy supplier and say, hey, can I have 30 kilowatt hours per day? And they say, yeah, absolutely fine, no problem. But that doesn't make sense when I then turn on my oven, because my oven takes over 2,000 kilowatt hours, and all of a sudden I'm under-provisioned. So I have to now run at 2,000 kilowatt hours and overpay, essentially. Well, that's fine, because the energy provider can give me a nice slider. And they can say, well, I can slide all the way down if I want to, and only slide it up to 2,000 kilowatt hours for the time that I'm doing my cooking. I thought that's pretty good, but chances are I'm going to forget to scale down when I've finished. It's a bit of a pain. That's okay. What they can do is they can auto-scale for me. So they can scale up when I need it, and they can scale down when I need it. Problem is, they turn around and say, well, that's fine, but you're being billed per hour. So every time I put the kettle on, it takes 3 minutes to boil a cup of tea, I'm being charged for an hour of consumption. And that's kind of crazy, and yet that is what the vast majority of cloud services still do today. To kind of show you what that kind of means in sort of in practical terms, we did a little bit of modeling at the beginning of this project. And we looked at a 10-year horizon. We looked at a lift and shift scenario. We've done a lot of work in Cosmos DB in the past. We love Cosmos DB. We thought, okay, let's model it in Cosmos DB. You can see lift and shift. After a year, we're up to £100,000 per year. After 10 years, it's $500,000. And the reason for that increase is because OceanMind retain all their data. They want that map that you saw. They want to be able to move the dial and actually see 10 years worth, what was the situation 10 years ago? What's the situation now? In kind of live kind of sort of experience. There's also, we've also factored in the growth rates of data. So they are seeing that there's going to be an increase of data over time as more and more vessels and more information becomes available. We look at Cosmos DB. Initially starts working out a lot cheaper. By the way, Cosmos DB is advertised as a serverless product. As I say, I love Cosmos DB. 37,000 bit cheaper, but actually by year 10, it's nearly $1 million. And the reason for that is because we were looking specifically at the SQL API. So if you know Cosmos DB, it's got a whole bunch of different APIs you can use. The SQL API has some geospatial capabilities, so we thought, hey, we'll try that. But if we modeled that out, we actually found that it got more expensive. And the reason being is that the storage is predominantly in JSON format. And as you've probably heard, and you probably know, it's quite an inefficient format. So what if we could take the problem and apply it to some more, I suppose, more commodity-based services. So something like Azure Data Lake Store, or Azure Storage, and Azure Functions. And these are closer to the more of the commodity model that I actually think is worthwhile. We ran, this is like a sneak peek into the future. We ran these, this particular key workloads, and we benchmarked them, and this is the numbers we actually came up with. So Data Lake Store is significantly cheaper. It's based on Azure Storage, so it is significantly cheaper. Azure Functions is actually ridiculously cheap, so £58 per month these are. So, well, you know, it's a no-brainer. So the problem we really have is, okay, well, these services are cheap, but we're losing out on a lot of functionality. The lift and shift had a very dedicated specialist geospatial database running behind it. Cosmos DB has got some great features. It's got really sort of groundbreaking SLAs. It's excellent. So is it possible we can replace those great services with something that's a lot cheaper? And that was our challenge. So if I summarize the service characteristics that we think are important, so zero administration, you probably heard about. Pricing based on consumption, which is the key part of this. Transparent scaling from zero. One of the interesting sort of side effects or downsides to these types of models is you're quite often limited in terms of the resources. They kind of run you in a sandbox, and the really sort of cheap SKUs, you're kind of sharing capacity with a whole bunch of other people who are running on Azure. And as such, you're limited, you're constrained by the amount of memory you can consume and the number of connections. So that's the other side of the story we need to be a little bit careful about. But we want the ability to be able to provision capacity if we need to. So whatever services we use, we want to be able to say, okay, well, actually, if for whatever reason we can't get our workloads running in, in our consumption-based model, maybe for that one workload, we might actually run it on a pre-provision capacity basis. And a lot of these sort of these serverless frameworks, or these functions as a service frameworks, can now run in containers, and that includes Azure Functions. And while we're not specifically talking about containers here, we're talking about actually running it on the Azure Fabric directly. That is another option for us if we want to be portable in terms of cloud. So another important point, really, is the scale of the problem here. So when we're doing lots and lots of small pieces of work, the cost and the time is proportional to the number of invocations and the number of messages that you're processing. So if you're just running a very simple application, sometimes it may not be worth optimizing. But when you're processing billions of messages a month, small optimizations can actually have a massive impact. Okay, so that's actually quite key. A key concept, a key thing that we really, really aware of as we went through, alongside the fact that we are constrained in terms of things like memory, number of connections go outbound, as I mentioned just a moment ago. So this is a typical pipeline for one of their key workloads. They ingest data from external data providers. AIS is the format of vessel track data. You can go and buy that yourself if you want to. Satellite imagery, in the cases of just images, those are binary formats, they get ingested. We need to do something with that information. We need to parse it into a format that allows us to do analytics. So parse those into vessel tracks, run those through some geospatial models, some feature engineering, and then finally run our ML models over the top of that to detect illegal fishing. And the challenge here is, can we do this with Azure Functions and Data Lake Store? So we're going to run a couple of demos. It's the first time we talked at NDC, and so we thought we'd do some live demos, so what could possibly go wrong? This is actually more like a pre-demo demo, okay? But I do get the ability just to quickly show you a little bit about Data Lake Store if you haven't already seen it. So Data Lake Store is as I said, it's built on Azure Storage, so it gets the same sort of features in terms of it's deployed in every region. But it builds on it by providing a hierarchical namespace, and that sounds really fancy, but all it really means is that you can create files and folders. And you can apply security rules to those files and folders, and that's really kind of important because when you think about actually partitioning the data within the system, we want to make sure that the person that's responsible for parsing the data only gets read access from the source data and write access to the target folder. So we can really get, really lock down from a security point of view. And folders, if you've done anything with Spark or any of those types of platforms, you'll be aware of the way we can use folders to remove the data that we're not interested in and only focus on the data that we are interested in. So here you can see we've got a raw folder. I'll quickly show you that. So we've got a raw folder. We've got this AIS folder. That's our source data. If you've done anything with Spark in the past, you might be familiar with partitioning by dates, and that's just really quite useful for time series type information such as this, where all the data for a particular time bucket goes into one folder. Here's an example file. It's an NM4 file, so it's a binary format. I can't read that just in Notepad. I've got to actually parse that before I can do anything with it. We've got another, these are known as file systems, by the way, so these blob containers. They're called blob containers. I think Azure Storage Explorer, which is what this tool is, hasn't quite renamed things from Azure Storage days, but it's actually known as file systems. So we've got in our data folder parse data. If I go into the parse data, we get a similar structure, partition by date. There's a Parquet file there. We chose Parquet. For this talk, it's not important. We've got some benefits in terms of compression. Parquet is better from a compressed point of view. There's other reasons why we may want to use that as well in the future. And if I jump out again, we've got this folder called projections. This will become apparent in a moment, but for now, just know that it's empty. It's got no data in it. And finally, we've got signals. And signals are the outputs. These are our features, our phishing alerts. These are the things which are driving the business. And again, for the benefit of this demo, just notice that there's nothing in there. Okay. Okay. So, developing a feature pipeline. How do we go about this? Now, as I say, I think if anything from this talk, I think this is the most important takeaway, really. What is the process we took? Lots of people, when they come across these types of problems, they focus on the data. They go, right, we've got some data from our data providers. Let's suck it all in. Let's process it. Let's clean it. Let's chuck it in a model that kind of makes sense. We actually took the completely opposite approach. We focused on the workload first. So, for example, vessels in proximity. Vessels in proximity is a really interesting feature that can be used in machine learning models. So that's the idea that two vessels at the same point in the same space at the same point in time may indicate some information that could be useful for detecting illegal fishing. What's interesting about focusing on the workload is that it provides us with a really clear need. It's a single unit of work. It provides us with a really nice test boundary. We know what outputs we really need, and therefore we can actually define what it is we want. And then also one of the problems, I think, or one of the fears of this approach of using functions are, well, the problem is we've thrown away this database, this geo-spatial database, and all this rich features. And now all we've got is C#. We're starting from scratch. And yes, I can understand that fear, but actually in practice, think about it. You can write your own code, whatever you want. You're not constrained by the platforms of old. You've got open source. You can have a look, and a lot of people who have been developing these great platforms actually open source a lot of their library. So you can just pick and choose what you need to solve a very, very specific problem. So once you've kind of defined the behavior and you've understood how you're going to solve it, it's then a case of, well, how do we solve the database problem? How do we how do we find the data we need? Because every single vessel coming in regularly, billions of vessel tracks coming in a month, that's crazy. So rather than rely on a database per se, why don't we just say what information at any given time does that processing need, and what is the optimum format for it to arrive? So ask yourself, if I was going to write the ideal file, just a file on disk with all the data I need in the right order, in the right way, formatted perfectly for my workload, that's got to be the most optimum solution. And if you think about it, files themselves, Data Lake Store, is a file-based system, essentially, but also they're quite easy to cache as well. So once we've defined our optimal storage for our particular type of processing, we can then work backwards and figure out where we're going to get that from and whether our providers are capable of providing that information in the time that we need, and we can do some experiments around that. If you repeat this, you end up with this. You end up with lots of very well-defined units of work, and you end up with those units of work owning the schema and the data that they need to operate. And as software developers, we've become quite used to doing this. It's kind of almost like a microservices architecture, really, if you think about it. You know, tight, really well-defined boundaries, testable boundaries. Analytics, for some reason, doesn't really do this so much. If you've done a lot of data analytics, traditional kind of data science stuff, they don't really kind of think in these kind of ways. So I think it's something that as developer community, we can really sort of start bringing our skill set to some of these more sort of traditional old school analytical problems. Data projections is quite an interesting concept. You'll see that what we're doing here is we're defining a series of data projections. These are our schemas, our optimized data sets. We're reading those out, and basically what we mean by this is we're taking raw data and we're projecting it out into the formats we need, okay, for our optimal processing. Important concept. So what about serverless machine learning? Well, if you know anything about ONNX, ONNX stands for the Open Neural Network Exchange. It's a specification that allows you to serialize, or defines how to serialize computational graphs. What's interesting about this is it allows you to train models in your standard tools that you're all familiar with. So you can train a model in TensorFlow, you can export it to an ONNX model, and then run that ONNX model for scoring or inference on anything pretty much. So Azure Functions, you can run ONNX models on Azure Functions. If you need Azure Machine Services, maybe you've got some GPUs that you need to rely on, you can use Azure Machine Learning Service. You can run on virtual machines, obviously. You can run on the edge, on devices. You've got all these different options. And again, it's not about saying you must run everything in serverless. We're saying is if you have the option, it's got to be a good thing, right? Finally, before I hand over to Carmel, I just want to talk about something else that's really important in our kind of learnings, really. If you're a data scientist, you'll be very familiar with being very, very strict with yourself about defining the hypothesis and the success criteria up front. What you do is you go away, and once you've got your success criteria, you go away, you try and build a model that actually meets that or proves that hypothesis, and you measure and adapt according to the results you observe. As software engineers, we're not as good at doing that, but we can treat it in exactly the same way. So can we process 1.5 billion messages a month for less than £10 in compute costs? Well, that's a hypothesis. Can we do it? The only way we're going to know is by trying and measuring through benchmarking and adapting according to the results we observe. It's a mindset change that I think we all need to get into as we start working in these kind of environments. So that's the theory. I'm going to hand over to Carmel to talk through some of the practical elements.
Right. Well, I've got a feeling in a few years I'm going to be looking back on this and going, yeah, the first public speaking I ever did was at NDC London, and people are going to look at me like, wow, that's insane. I know. But here we are. So, so what did we need to do to build up these processing pipelines for the analysis we needed to run? So the analysis I'm going to focus on is detecting vessel proximity. So that means finding ships that are within a certain distance of each other for a certain amount of time. And this is important because that was information that fed into Ocean Mind's machine learning models. So the way we need to do this was to take this vessel point data from ships checking in at regular intervals, and from that build up vessel tracks and then run the proximity analysis over those tracks in order to detect these events and raise alerts based on that. So because we decided to take the serverless approach rather than using these IS sort of out-of-the-box solutions, we had to build up this analysis ourselves. So the way we did that was we took 2 consecutive vessel points in a track and using the velocity in both the X and Y direction, built up equations for the ship's position over time. And then just by Pythagoras, the square of the distance between 2 ships is just the square of the distance in their position in each of these directions. So using this equation on the right, we could then work out the times at which 2 ships came into contact with one another, and again when they left that contact distance, and therefore work out sort of how long the ships were in contact with each other and raise alerts based off of that. The issue with this analysis is that comparing 200,000 vessels to every other ship in the ocean is a really expensive thing to do. So vessels check in about every 2 minutes on average, so that's about 300 million comparisons a second. So we really need to find a way to reduce the amount of comparisons we needed to make. and identify likely candidates for this proximity analysis. So, when we were researching geospatial algorithms, we came across a paper about R trees, and R trees are a data structure for storing and indexing spatial data. So for our analysis, what we did is we took each sort of little segment of vessel track and found the bounding box for that segment. And then sort of by focusing in on various parts of this R tree, we could find overlapping bounding boxes and therefore find segments of vessel track which were within a certain distance of one another, and therefore are likely candidates for these proximity events. The way this works, so when new data arrived, so we wanted to store the data in a way that would be easy to build up these R trees, and the best way to do that would be to store the data so we could really quickly read out these vessel tracks. So the way we did that was when new data arrived, we first partitioned it up by date. So we'd split this data up into date windows, and then all the segments of vessel track within those date windows would just be compared to tracks within the same time frame. And then within each file, we'd sort the data by vessel, and then for each vessel, sort the data by timestamp. So in this really simple example, this just means that the first half of each file will be the track for vessel 1, and the second half will be the track for vessel 2. So just to show you what one of those files look like, so here we've got a Parquet file. This is displayed in, This is displayed using a Databricks notebook. Databricks is a really good tool for sort of exploratory experimental analysis and good for viewing Parquet files, which can be quite difficult to view. So here you can see you've got an ID for the first vessel, and then the track for that vessel. You've got the latitude and longitude for the vessel at each of these points. And then in the second half of the file, you've got a track for vessel 2. We've got a system in which we ingest data, we then pass that data, we project that data out into these projections, and then run the analysis over these different projections in order to then be able to query the insight we need. We can have multiple projections with this analysis, so if we, as Jess was saying, if we had different analysis that would use different types of projections, we could then create a second projection in order to support that. So we've got a lot of steps, and we need some way of being able to orchestrate all of these steps. And this is where durable functions came in. So durable functions are an extension of regular functions, which do sort of stateful orchestration of multi-step processing. State is stored as this processing progresses because with these long-running operations, you need to be able to restart the processing should the function host restart. And you do this processing by calling out to asynchronous steps within the processing, and therefore can build up quite complex process from small units of work. Durable functions also allows you to control the parallelization within the system. So built into it is fanning in and fanning out as you can parallelize different parts of the processing, and this will fan out to multiple functions instances as and when they are needed. So we used a few different patterns while building up the processing. So function chaining means to take the output of one function and use that to feed the execution of the next. So using this, if you've got these steps that we need to orchestrate, you can take the output of one and use that to feed the execution of the next one and build up this quite complex processing. Also built into durable functions is support for the async HTTP API pattern. If you don't know, this pattern basically means you kick off a long-running operation via an HTTP request. You're then redirected to a URL which you can then poll for the state of the long-running operation. And this is supported out of the box in durable functions and integrates really well with Azure Data Factory, which will automatically pull the function for completion. I already mentioned that you can control parallelization within the system using the fan-in, fan-out pattern. So this means that if you have processing that can happen in parallel, you can fan out, and then if these result needs to be aggregated, you can fan back in and do any of the processing you need to do. So in our system, this looks something like this. So when new data arrived, if we had multiple projections that needed to be run, we can parallelize that because the projections are completely independent. So we can fan out to multiple projections, and then within each projection, each of the partitions are again independent, so we can fan out again. and then aggregate these results, so aggregate, say, these proximity signals, and run any overall analysis and query that insight out the other end. So I'm now going to do a demo of the orchestration running, and this is where it could all go horribly wrong. So here we have a function host, which is running our orchestration function, and usually this would be kicked off by a new file arriving, and that would automatically start the orchestration. I'm going to do it by hand. So a good start. All right. I'll give it a second. Right, we do have a pre-canned version of this demo, which I can try if this does not come back to life. It's Postman's not responding. Right, I will just play the video. That's what I get for trying to do a live demo, isn't it? So here we have the orchestration. And so usually this would be kicked off automatically, but here we're just sending in a request to it. So that request has the file that's just arrived and the contact distance, so that's the distance at which we say two ships are within in contact with one another. And we can see that we are projecting this file out, so we can see on the right that the memory for the function is increasing, so that's as the data is being read in. And we should see that these projections should start updating. So these projections are actually updated in series at this point, so each partition is updated in series because so we kind of need a long-running track through all of the files. So say you have you had one file and you had the vessel track throughout that file. The next file needs to know where the ship was at the end of the previous file. So we went through and added the last data point from the previous file to each of the subsequent files, and then you get this continuous vessel track throughout. But yeah, so once all these these partitions have been updated, we can then sort of fan out and start doing the actual proximity analysis over each of these. So that'll be building up the R trees and then running the sort of more detailed proximity analysis over the candidates found by the R tree analysis. So we should see, and we definitely should because the demo has been recorded, that this gets a lot noisier in a second. There we go. As we fan out to multiple function instances and then build up the R trees for each partition file, and then find for each of those candidates whether there's been any proximity events within that time. This is actually running slower than it does in Azure because this is all done over the internet because we're downloading and uploading these files as we go, whereas in Azure, sort of, it's all done on server, so it would be actually a lot quicker to read and write those files. But yeah, so this is creating new files in the data lake. So this will have already created the projection files, which will have the data organized into vessel ID and then by timestamp within each vessel, for each vessel, so those vessel tracks. So we should see the projection files in this folder. And those again are partitioned by time, so you can quickly read out the partitions for the data for the time in which you're searching proximity events. And then we should also have, for any time partitions where there were proximity events, we should have a signal file, which will have details of the two vessels that were in contact, the start and end of the proximity event, and where each vessel was at the start and end of that. Yeah. So, once we had built up all this processing, we needed to then optimize for a serverless environment. So as just mentioned, in Azure Functions, you've got certain constraints on what you can run. So we've got memory constraints. You can't go above 1.5 gigabytes of memory on functions on the consumption plan. And also, Azure Functions pricing is based on time of execution and also the memory used within that time. So reduction in memory would be a really important thing. In order to sort of check that any changes we made to the solution were actually an improvement in either performance or cost, we needed to benchmark, and we wanted a way to build this into our system so that it was really integrated with the change management within the system. So we built a small tool which used application insights to monitor the running of the orchestration in Azure, and then we could use this to sort of assess any changes we made. So in order to optimize for the serverless environment, we needed to understand what factors affect performance in .NET. And so we were optimizing .NET here, but Azure Functions, you can run Python, you can run Java, JavaScript. This is focusing on .NET, but optimizing for these serverless environments, that applies to any language. So obviously, the first factor that affects performance is the actual processing logic. If your code is doing loads of unnecessary work, it's clearly going to take longer than it should. But something that people often overlook is the effect of garbage collection. So garbage collection, most of you probably know, is the process in .NET of clearing up unused memory. And the way that works is it suspends all processing in order to count which references are still in use. So clearly, the more garbage collections that are triggered, the less time is spent on the actual processing. So it would, from a performance point of view, we really need to reduce the amount of garbage collections that are triggered. And the way to do that is by allocating less memory to start with. So we used several techniques for reducing the amount of memory used, and the first of those was list pre-allocation. So in our processing, we ended up with big lists of vessel track segments ready for comparison for proximity analysis. And if you initialize, so lists are built on arrays, so obviously it has a level of extraction over that where you can just continuously keep adding items. But these lists are built on the arrays under the covers, and arrays have to have a certain size when they are allocated. So if you initialize a new list and don't give it a size, it will default to a value of 4. If you then exceed that size by adding 4 more items, it will allocate a new array of double the size, so 8. So this gets really bad when you have really big lists of stuff, because you suddenly, if you exceed the capacity, it will allocate a list of double that size. So you will suddenly have almost 3 times the memory you actually need, and you end up with these massive memory spikes. And we saw this in our processing, where we'd suddenly just run out of memory. And we couldn't work out why for ages, and it was because of this massive increase in memory suddenly. So the way to get around this is to specify a size of the list when you first allocate it, and you then avoid the issue of unused memory and also of these big memory spikes. The next sort of technique we used was actually not using lists at all. So we used IEnumerable and stream processing to mean that we never had to store this entire list in memory. And this only really worked for our processing because we could sort of aggregate the results as we went. So we could build up these proximity signals without doing any sort of whole list operations. But this meant that we never had to store the whole list in memory, and therefore reduced the amount of memory that was in use at any given time, and made us far less likely to hit into these out-of-memory exceptions. Another really important thing to consider is the arg stream reference and value types. So in C# in a 32-bit process, a thing class will use up 20 bytes of memory. So that's 8 for the data, 4 for the pointer to that data on the heap, and 8 for the object header on the heap. If you instead use a struct, which is a value type, you will only use up the memory needed for the data. However, in our processing, we had these. We needed to compare 2 segments of vessel tracks, so we ended up storing pairs of vessel tracks that we needed to run the analysis over. So we ended up with quite a lot of copies of the same data. So if you have a class, a reference type, each additional copy will only take up an extra 4 bytes because you just store another pointer to the same bit of data on the heap. With a struct, every extra copy will have its own copy of the data, and therefore will be another 8 bytes. So you can see as you get more copies of the same object, you end up eventually using more data using a value type than a reference type. And in here, you'd need 5 copies, but this gets more extreme as your objects get bigger. We ran into this because I was trying to reduce the amount of memory we were using and thought, oh, well, structs are small on classes, so I'll just change the value, change it all to use structs instead of classes. And this was where benchmarking came in really important because I made it much, much worse. So yeah, nothing to consider. And the last one I want to talk about is a span of T, which is a relatively new feature of C#. Spans are a way of indexing into contiguous memory on the heap. And so this is an example from Ian Griffith's new book about C#8, and I have stolen it. I did ask him. So you had a string which represented a URI, and you create a new URI object. You can access different parts of that string using the different properties on the URI object, but each of these properties represents another string which has been allocated on the heap. So you actually end up allocating quite a lot of strings in order to access different parts of the memory. If you instead use a span, just to index into the first 4 characters in that string, you sort of can access that memory directly, and because spans are reference structs, these are allocated on the stack, so you don't cause any extra allocations. So obviously this type of processing has its own complexity, and there's sort of other challenges involved in writing code like this, but in this sort of serverless environment, especially in big data, where, as Jess was saying, like these really small performance improvements can have a massive impact when you're processing millions of messages. Processing like this, sort of really low allocation processing, can be really integral to getting a sort of cost-effective and also performance solution. Yeah, so I'll hand back over to Jess to summarize.
Oh, a bit of time. Can I have the little clicker, please?
Oh, sorry.
That's all right. I think it was really interesting sort of hearing Carmel talk there. I mean, it sounds complicated, but they're actually simple things. Simple approaches, simple practices that we can apply time and time again. And once you get used to it and get familiar with it, it kind of becomes second nature. But I think what's important about this is not to distract away from the fact that actually the actual approach, the pattern is actually really simple. It's just a case of, okay, finding the workload and then optimizing it for your constraints. And you know what? If you can't get your workload to run under the constraints, then you do still have options. But there are significant benefits, obviously, in terms of if you can actually make it work. So the takeaways from this are, the commodity cloud services enabled OceanMind to process more data in near real time while drastically reducing operating costs. And for them, that was absolutely important. And I think, hopefully, if you can take away anything as well, this wasn't a trivial example. This is actually quite a complex scenario. Resource constraints need to be managed through experimentation and benchmarking. Carmel mentioned a few times where we broke functions. The consumption plan basically said, no, you can't do that. And we're like, okay, well, let's keep going. Benchmarking is really important, especially in terms of regressing. You can make a small change, as Carmel mentioned, and all of a sudden, you're back to square one. Cheap cloud storage can actually be a really good option. You don't necessarily need sort of generic databases. You don't need SQL Server necessarily. It has its place, don't get me wrong. As I say, Cosmos DB, fantastic product. But this situation, we just didn't need it. And that was down to the approach we took in terms of solving the problem. And that approach was using data projections as opposed to sort of running queries as and when it needed to be run. There's us, by the way. If you're interested in learning more, as I say, this talk, we had so much to talk about. If there's anything here that's of interest and you want to catch up with us, just ping us, DM us, or whatever. Get hold of us, or catch us after this talk. This is Ian Griffith's new book. If you're interested in some of the newer techniques, especially around performance and stuff that Carmel mentioned, C#8, really good book. And some references I'll leave on the screen for you. During the process of doing this piece of work, we didn't touch upon it, but we created our own AIS parser. So if you're doing anything like this data, if you've get your hands on any AIS data and you want to parse it, we've written an open source .NET parser. This, I believe the benchmarks for these were, I think it can process 7 million records a second on a single core. So it's properly, it's all the techniques that Carmel mentioned plus more. So it's properly optimized. So please have a go and please contribute if you want to get involved in that. A couple of blog posts that Carmel put together, which talks about some of the things she's mentioned in today's talk. Please have a look at her blogs. There's also this R-tree paper. So there's a couple of references actually on the internet. This is one of them. So R-tree is also referenced for the geo-spatial library, which Microsoft I've put a lot of material out about. Goes into things like how SQL Server does its geospatial work. Uses the same technique, so please have a look at that if you're interested. If you're interested in OceanMind, they are a fascinating organisation, really great at what they do. There's a really nice case study under the programme of Microsoft AI for Earth. Microsoft run this programme. If you are a not-for-profit, if you are doing some really cool stuff in the environment and you want to get involved, let us know. We can connect you up with the right people for Microsoft AI for Earth. They help and support in terms of funding and that. So that's a really good video to look at. If you are into data strategy and sort of general strategy and how to talk to business stakeholders about how you want to, transform your organisation with data, I highly recommend this video. It uses a technique known as Wardley mapping. If you've not come across it, I strongly advise you look it up. It's a really good strategy. It talks about the strategical reasoning behind how we came up with the architecture, what bits were the bits we really wanted to optimize, why we chose serverless over non-serverless, and how we can communicate that, as I say, to the key stakeholders within the business so it kind of makes sense to them. So again, I'd have a look at that as well. We've got a few minutes for questions. So any questions? No, I'll take that as a good sign then. Please have a chat afterwards if you have got questions and you don't want to just stick your hand up, or catch us afterwards. But thank you very much for coming.